you do about it? What you can do about it, it depends, of course, on the material. Intergranular fracture will ordinarily lead to a very, let's start out with intergranular fracture, because intergranular fracture may happen in steels and can also happen in face intercubic materials. Aluminum is susceptible to brittle behavior by intergranular fracture if you contaminate the grain boundaries of such things. So begin with intergranular fracture. If we're going to get a ductile material, and if intergranular fracture is a problem at our operating stress or operating temperature, we've got to get rid of it. How do we get rid of it? Well, I'll tell you how to get rid of it in just a minute. You figure out what's causing it and get rid of that. But if you suppress intergranular fracture, see what happens here. In a face intercubic material like aluminum, if I do something to raise the stress for intergranular fracture, I suppress the ductile brittle transition. I can make it just go away. We use aluminum at 4 Kelvin all the time with no concern at all about brittle fracture. In body intercubic materials like steel, what will happen if you suppress intergranular fracture is that you will change the fracture mode. You'll still get brittle fracture. You'll still have a ductile brittle transition. It'll be lower. And now below the ductile brittle transition, you'll see transgranular cleavage. What do we do about intergranular fracture? Well, the first thing we've got to do is figure out why it's happening so that we can get rid of it. Almost the vast majority of examples of intergranular fracture occur because there is some contamination of these grain boundaries that causes them to come apart rather easily. There are a lot of materials, sulfur, phosphorus, arsenic are classic examples. Sulfur and phosphorus are the ones that are really hard to get rid of because they just naturally come in the processing of steels that can lead to serious intergranular fracture. They are attracted to grain boundaries, they're surfactants, they weaken the grain boundaries, and the materials come apart. So you see fracture surfaces that look something like this. These kinds of materials, there are really 3 cures. What you've got to do is get this stuff out of the grain boundary. There are 3 ways of doing that. One is you can purify the steel. You can get the sulfur down to extremely low values. And that's actually done now in commercial steels. When I first started doing this kind of thing, it was economically impractical to make commercial steels that had really low sulfur, so we had to do other things. And they do it all the time, surprisingly pure material. But it is still, there's a limit to how pure you can make the material, and it costs you money to purify the material. So there are 2 other things you can do. One is heat treatment. With heat treatment, you're playing kind of a dangerous game, but you can play it. There is a temperature range at which the segregation of impurities like sulfur to cause this kind of brittle will happen. If you're at high temperature, you're not going to get much segregation to the grain boundaries because entropy will drive all the sulfur away. If you're at low temperature, you're not going to get much segregation to the grain boundaries because diffusion is so slow it'll never get there. There is an intermediate temperature called the embrittling temperature at which the impurities will go to the grain boundaries and cause this disastrous effect. So if you can simply heat treat the steel so that you avoid, or the aluminum alloy, so that you avoid this embrittling temperature, then you can be safe. That's a very iffy way to do things because the embrittling temperature is sensitive to a number of variables. It's rather hard to predict and control. So you can do that, but you're playing a somewhat dangerous game. The way that it's normally used these days is a method called gettering, well, high purity. And on top of that, to make sure you don't get this problem, you do what's called gettering. You introduce an alloying element which interacts with the bad actor like sulfur and gathers it into a precipitate. And if you do it right, you can not only make this precipitate form, make it very stable, so all the sulfur is gone in the precipitates. You can also choose your alloying elements such that these precipitates are nice little spheres, so they don't introduce much in the way of extra stresses, and in that way you get a very good material. So they do gettering, and then they use what's called inclusion shape control to get them in the right shape, and that is the way that you really protect against intergranular fracture these days. The best additives for sulfur and phosphorus are rare earths. Rare earths like cerium, lanthanum, so on. Cerium in particular, cerium sulfide is a very stable sulfide, very, very good material. The problem with that, of course, is these rare earths are very expensive. There is, however, in the iron ore fields up in Michigan and a couple of places in the earth, a byproduct of the processing of ore, which is called mish metal. It is a mixture of rare earths. It costs a lot of money to refine the individual rare earths out of it. So this mish metal is not particularly useful for things like TV screens and so on, where you use rare earth materials. However, it's great for gettering things in steel. So it's the mish metal that's used as the additive to do this. There's another possibility here. There are some materials, classic examples are iron manganese alloys with manganese content, nickel-free aluminum, and some other intermetallics, where the intergranular fracture just appears to be inherent. The stuff just breaks on the grain boundaries. And in that case, you want to take the opposite approach. You want to add something to the material that is a surfactant that goes to the grain boundary and acts to glue them together. There are fairly simple thermodynamic criteria which tell you what such materials might be. A very good one is boron. If you add a little bit of boron to a 12 manganese, iron 12 manganese alloy, the ductile brittle transition, which was above room temperature to begin with, will drop to below liquid nitrogen temperature on the addition of 1/100th of a percent boron, because the boron just goes straight to the grain boundaries and glues them together. That's I actually had a patent on that. Nobody wanted to do it until the patent ran out. All kinds of people are doing it now. Didn't make much money off that patent. If you beat intergranular fracture, then what you're left with is the inherent fracture, which is transgranular. You get nice flat faces that look something like this. This is in a steel. Even the microstructure of martensitic steel is such that even though it looks like we have all kinds of grains here, they're actually crystallographically identical. So essentially this is a single crystal. And here you see the cleavage cracks going across the grains. Iron BCC metals cleave on 100 planes. And here you see the flat 100 planes. So what are you going to do about that? Well, if you can refine the effective grain size, if you can make sure that these coherent regions that can cleave together are very small, then you make it difficult for a cleavage crack to propagate because it has to be constantly stopping and starting again as it hits the boundaries where it wants out. So the way that we fight transgranular cleavage is to refine the effective grain size. I keep using the term effective grain size because sometimes there's some subtlety in, like here, what the grain size is. You see these little bitty things that look like grains and they aren't. So you have to decide what really is the grain size, and then you refine it. Now, when you refine the grain size, you actually do 2 things. You raise the fracture stress and you raise the yield strength. Both of them, interestingly, go up like d to the minus 1/2. Making d smaller raises the yield strength and raises the fracture stress. So you change this situation, this strength curve and this fracture curve, to the situation shown here. The yield strength has gone up, the fracture stress has also gone up, but the ductile brittle transition has gone down, provided that this effect on fracture is greater than this effect on strength. And in steel, it almost always is. So you control the ductile brittle transition in things like Arctic pipeline steels and so on, ship plates for ships that don't crack in Arctic waters, by controlling the grain size. In fact, it leads to a very, very interesting thing. This is about the only way that you have a situation in which both the fracture properties and the strength property improves together. If you refine the grain size, the yield strength goes up, but the ductile brittle transition goes down. And here's a plot just showing a great many steels developed over the years. And as you refine the grain size, sure enough, as the strength goes up, ductile brittle transition comes down, and you can get these things out here with very high strength and very low ductile brittle transitions by making them with very fine grain sizes. the way that you control the strain. All right, what happens in the ductile mode? Suppose we've got the ductile brittle transition down. We still want to get the strength, the toughness up, but now we're fracturing in the ductile mode. What can we do then? Well, let me just mention a couple of things. First of all, there's this universal curve that shows the toughness going down as the yield strength goes up. And I said I would explain that to you, why that happens. And it happens for the following reason. The plot I showed you earlier of the concentration of stress at the tip of the crack is a bit of an oversimplification, particularly when it comes to a ductile material. Because if I have a ductile material and I load up here at the crack tip, I'm going to get some plastic deformation at the crack tip, and that will tend to lower the stress. The net result of that is that if I actually plot out the stress ahead of a crack in a ductal material, I'll find that it increases slightly as I get ahead of the crack and peaks out a little bit ahead of the crack right here at this value sigma m, then drops back to sigma a. Since that value sigma m, well, let me mention the stress state here at the crack tip. You're in a very confined space. You can always resolve the applied stress into the sum of a shear, effectively, and hydrostatic pressure. Ahead of the crack tip, because of this confinement, you actually have a significant hydrostatic tension. That is, it's trying to pull apart in all directions hydrostatically. That hydrostatic tension cannot be relieved in any way other than fracture, because plastic deformation is in shear. It doesn't change the hydrostatic component. So the stress actually at the crack tip, the stress that is not hydrostatic, involves a shear stress, and that will cause the material to yield. So it will relieve itself. It will drop back to the yield strength. The other stress is hydrostatic. So the actual stress here at the crack tip, the sigma maximum, is the sum of the yield strength and the hydrostatic pressure. There's a negative sign on the hydrostatic pressure because we always measure pressure as positive when it's compressed. In this case, we're in tension. Stress is measured positive when it's in tension. Pressure is measured positive when it's in compression, and that leads to the sign over there. Because of the constraint and because of the development of this hydrostatic pressure, this sigma m, it depends a little bit on things like how well the material work hardens. But you can do elastic plastic solutions for the stress here at the crack tip, and that sigma m turns out to be something like 3 to 5 times the yield strength. So as the yield strength goes up, the maximum stress you can develop at the crack tip goes up proportionally to it. Since the material fractures when sigma m hits a critical value, basically when P gets big enough to cause it to break, that means that the toughness is going to come down as the yield strength goes up because the maximum stress at the crack tip goes up as the yield strength goes up. And therefore the material fractures more easily. So that's how this thing comes down. But now what can I do to improve the material? I would like to take this whole characteristic curve and push it up. I'm going to do that. Well, we already talked about the mechanism here. Ductile fracture happens because inclusions ahead of the crack tip either crack or decohere, forming voids. The voids get together and grow back into the crack tip, causing this ductile surface that we see down here. The thing that causes these voids to form are the inclusions. Now, it does matter what the inclusions are. The bigger the inclusions are, the bigger problem they are. But once we get the conclusions down into the micron range, what really matters is what their density is. You want to make a better material. What you basically want to do is to get the inclusion count down. And if I focus on the inclusions which are large enough to nucleate voids, it turns out the fracture toughness goes like a yield strength. It's proportional to the yield strength over the square root of the inclusion count, number of inclusions per unit volume. The square root of the inclusion counts is actually just the number of inclusions per unit area in the plane of the fracture surface. We want a better fracture toughness. We want that number down. And here's a specific example of that. This is one of the best strength toughness alloys in the world. It's Aramec 100 made by Carpenter, invented by Carpenter, made by several people now. It's a very high alloy steel, and you use it for things like landing gear and other situations that take very, very high stresses. And here's a standard strength toughness characteristic for, well, this is applied against the ultimate tensile strength, this is applied against the yield strength. And shows the strength toughness characteristic for this Aramec 100. They made an ingot, which we happen to get hold of, that for reasons that they've had trouble reproducing, had an incredibly low inclusion count. So here's the normal behavior for Aramec 100. Here is the third heat they made, which was normal. Second heat they made had high inclusion count and therefore very low toughness, but they made heat number 1, which had an almost 0 inclusion count, and you see the fracture toughness is way, way above the characteristic curve. So the secret, if you've got a material that fractures in the ductile mode, the secret to getting very, very good toughness is straightforward. You just get the inclusions out as best you can. You can never get all of them out, but you can get the inclusion count very low, and if you do that, it also helps if you have the inclusions the right shape, if they're spheres instead of flakes or something of the sort, and it helps if they have a certain other property. But basically, the simple message is just get the conclusions out. Hard to do. Okay, that essentially talks about what fracture toughness is and how we can control it metallurgically. Now let's go back to the engineering side and talk about what we have to do in order to use it and what other material threats there are out there. And I'll just introduce this briefly today, and we'll cover it in our final lecture, which is on Friday. Remember that you're going to get fracture when the stress hits sigma star c, which is the geometric factor of the plane strain fracture toughness divided by the largest crack that's present. Incidentally, this is a homework problem. I can kind of tell you the answer because it's here. Suppose you have a brittle material, and suppose you take the brittle material and you break it. Well, what has that fracture done? If it's a brittle material that doesn't yield, the fracture doesn't happen because of any deformation in the material. What you've done is you've located the worst flaw in the material. That's why if you, now I don't know if I put this on homework, I've used it on exams before. It's a simple little experiment. Take a glass rod, okay? Put it in a machine, pull it until it breaks. Now test either half of the glass rod. I can absolutely guarantee you that either half of the glass rod will be tougher, have a higher breaking strength than the original glass rod did. Because the original glass rod broke where A was biggest. The two halves of the glass rod have smaller A's. Therefore, they're going to be tougher. There was a problem when they were first trying to lay fiber optic cable undersea that people like Bell Labs, who was trying to do that at that point, ran into, and they racked their brains about how on earth do we inspect the cable so that we ensure that we don't have critical cracks and it's not going to break because it's very hard to get down into the sea and repair it. Some very clever person came up with an incredibly simple solution. He said, look, you don't try to make the cable so it won't break. You break it. The nice thing about glass and optical fiber is you can re-weld it very easily. So you take the fiber and you break it. What's left is now stronger than the original fiber because it doesn't have as big a flaw. You weld it back together, assuming your welding process is okay, it's now stronger. You break it again, and you just keep breaking it until finally it has a strength above the design strength that you wanted it to have. So sometimes you can use things like this in manufacturing in surprisingly clever ways. So, well, the problem you run into in the one sentence and then I'll let you go. The problem you run into in using these non-destructive testing procedures is that you are testing the part as manufactured. What's got to keep you up at night, if you know that there are mechanisms available, is what happens if I put this part, which has been nicely inspected, very safe, in a critical application, no cracks in it, and all of a sudden cracks begin to grow, like worms eating up my material. So that something that is perfectly usable suddenly fails. And you have probably experienced that, or you certainly will at one time or another. It's not at all uncommon, for example, in an automobile. Everything works absolutely perfect, and all of a sudden you get something breaking. Even sometimes an axle or something, just out of the blue. No unusual load, nothing, just bam, it breaks. That's the problem known as fatigue, and that's what we'll talk about in a couple lectures. See you then.